All goes according to plan, this should be a really short and also very confusing video. I just wanted to highlight some of the reasons that we have to talk about molecular orbital theory as organic chemists, which for the most part we can kind of escape from the vagaries of this theory. But sometimes we're going to have to refer to it. So what I've tried to do is I started off with kind of the simplest examples first, and then we'll just show the absolute mess that kind of happens as you get not very much more complex. And then what we'll do is we'll show kind of the couple of ways that we're going to be using MO theory in the class. So the first thing to know is that if you take a look at the molecular orbital diagram of hydrogen, which is this is a pretty good picture here, there's the bonding molecular orbital that is filled, right? So that's what contributes to the bonding order. And then you can see that the anti-bonding order is not filled. One thing which kind of was left off a little bit in the introduction video that I posted that I would have liked to have seen a little more talk about is the importance of phase in your atomic orbitals. So if the phases match, keep in mind that two orbitals, if they're similar in energy, right? So these are both the same energy because they're both atomic hydrogens. When they come together, if the phases match, right, they're both blue, let's say, you actually end up with an increase in the probability that you'll find electrons in this region between the two atoms, and that's what we call a bonding molecular orbital. This is what's called a sigma bond. Hydrogen, like I said, is really simple. And so the fact that those two hydrogens come with their single electron in the uncharged state, you kind of throw them both into the bonding molecular orbital. We don't have enough electrons to put into the anti-bonding molecular orbital, so that's why this thing is described as two H's bonded together, right? And so in the covalent theory, this whole entire picture is included in just like an H with a line and then an H, but it's actually a lot more complex than that. So the reason I go so much into hydrogen is because this is like obviously the easiest case, and it allows us to talk about two concepts which are both associated with what's called frontier molecular orbital theory. And so the way I understand frontier molecular orbital theory is that everything that happens in organic chemistry, or any chemistry quite honestly, is the interaction between one atom's highest occupied orbital, right? In this case, it's a molecular orbital, and another type of molecule's lowest unoccupied orbital. In this case, it's a molecular orbital, of course. So one of the kind of main themes of what we're going to talk about eventually is that organic chemistry is all about nucleophiles approaching electrophiles, or things with electron density approaching things without electron density. And so what we can see here is that really that same exact kind of nucleophile electrophile theory that we'll understand a lot better in the next couple of weeks is really the nucleophiles are having their homos interacting with the lumos of the electrophile, right? And so it turns out that the two phases, like this idea of this anti-bonding molecular orbital having opposing phases, it turns out that in order for a nucleophile to truly interact with this H2 molecule is you have to match those phases in the HOMO of whatever the molecule that happens to be attacking is. And again, I know that's totally crazy to think about, but it's going to be something that, like, as you get better and better at organic chemistry, will become more and more prevalent. So here's a picture of H2, right? Important concepts to know here. Lowest unoccupied molecular orbital is like the orbital that is the most accessible energy, that is like right next to the highest occupied molecular orbital, and that kind of frontier is where all the chemistry happens. Okay, so let's take one step a little bit more complicated. So we just went up one quite small level in complexity in terms of molecule, and notice what happened to this molecular orbital picture. It got crazy fast. You've got S's interacting with S's. You've got P's interacting with P's. And depending on their orientation in space, right, you end up with mixing together those wave functions such that it's the wave function times its complex conjugate, which you'll talk about in quantum mechanics. And I am not going to talk about much more than that here. We can think about it essentially that you square the wave function, which describes that electron, and when you square that thing, you end up with these probability pictures for finding electron density. So you can see that there's a lot of different bonding molecular orbitals and anti-bonding molecular orbitals, right? And so this guy is a bonding molecular orbital, another set of bonding molecular orbitals. These are antibonding, that's antibonding. And so each one of these, the point is, has kind of like a different look, right? The phases are different. So the important ones that we would talk about if we really wanted to build on this was if fluorine was going to act as a nucleophile, we would be talking about its HOMO, and we'd have to look at the actual overall picture of these two different things and their phases and energies and how that thing would interact with the LUMO of something else. Or alternatively, if you're going to react with a fluorine, you have to make sure that your HOMO, right, the nucleophile, reacts with fluorine as the electrophile, has to somehow match the phases and energy in this particular LUMO. So I'm not going to beat you too hard with this, just to tell you that, obviously you can see that this thing is fairly complex. It might be easier to just have two fluorines with a line and a couple of, 6 pairs or 6 lone electrons on either fluorine. That's covalent bond theory. You can see how much more complex molecular orbital theory gets. Here is something so complex, carbon monoxide, right? 2 different atoms coming together, but now you'll notice that their orbitals are the atomic orbitals, I should say. Let's just concentrate on the 2s. Right? Oxygen is so much smaller because oxygen has another proton in the nucleus that tends to make these energies far lower in terms of potential energy, relative to carbon, which is much bigger because it doesn't have as much kind of like pulling power on the orbital. We'll say that anyway. And so you can see that what can happen is this really horrible mess, right? Where not only are the 2s orbitals interacting, they're close enough with the right phases to interact into bonding and anti-bonding orbitals, but you also get mixing in of these other p orbitals. And so what's happening here, like all these complex interactions that really is a difficult computation even for supercomputers. Even today's supercomputers are really limited in terms of the molecular orbital picture. You have to use so many different approximations, all having to do with those wave functions and how we treat them. And so like I just wanted to show you like the complexity of just CO. And then in this next slide, I'll show you just kind of a really common type of organic, really simple organic molecule and how totally nutso crazy it looks. You do not need to understand this, but I wanted to show it to you anyway. This is what it looks like when a simple kind of organic-y thing, in this case it's a phosphine, interacts with a metal. And this is what just the picture of kind of the frontier molecular orbitals look like when you plug it into a computer. There's no real good way to predict this, right? And so what we're going to do in organic chemistry is obviously we don't have access to supercomputers. What we're going to do is we're going to, when it's convenient for us, right, we're going to, maybe switch to like the covalent bond theory with resonance so that we can answer some of the very same questions that the true answers for which are actually contained in molecular orbital theory. But then when the covalent bond theory just isn't enough, we'll just very briefly make some approximations and we'll switch over to molecular orbital theory, as we're going to see in the next couple of slides. So when we talk about benzene and aromatic chemistry, we're going to have to revisit some of these molecular orbitals. There's just kind of a picture of just the pi molecular orbitals of benzene. Notice that we left off everything except for the pi orbitals and the pi electrons, right? And so, for instance, in terms of understanding why benzene's so incredibly stable, well, it actually turns out, having to do with molecular orbital theory, that you've completely filled all of the bonding pi orbitals and none of the anti-bonding pi orbitals, right? Because we've got those 6 electrons that you can see there of those double bonds, and we throw them into all these bonding orbitals. But in terms of the HOMO and LUMO of benzene, you can see that we've got some kind of like semi-understandable patterns. One of the things you'll notice is as you go up in energy, your number of nodes increases. So in other words, the places the electron can't exist increases. I really like this slide because it includes kind of a static picture of what those molecular orbitals look like, right? And so in other words, if I threw 2 electrons into this orbital, the lowest bonding molecular orbital, you can see that they spend kind of, we're 99% sure we're going to find them either in this thing or underneath is kind of a similar donut shape And then, you've got something with one additional node. Right now we have a node right there, and then you can't see it, but a node kind of bisecting that thing in parallel to the screen. And then you got this other orthogonal molecular orbital. Orthogonal just means same energy, but a different orbital. And so you can see the same number of nodes, and then obviously more and more nodes come to play. So the things that are going to be able to interact with benzene is again, the nucleophiles are going to interact with the LUMOs, and if we're going to be a benzene interacting with with an electrophile, that's going to involve the HOMO of benzene. So just to kind of know that we're not totally out of the woods, but we are going to keep revisiting the picture of these things, these molecular orbital pictures. Another time when we'll talk a little bit about molecular orbital theory is, again, we're only going to be talking about the pi molecular orbitals. That's for something called hexatriene, which hopefully you can see that there, right? And so there's the covalent bond picture, and you'd be thinking, oh, awesome, that's pretty easy, right? All I got to do is put some squiggles and some lines alternating. Well, it turns out the true picture of this thing is best understood with this molecular orbital set here. And so you can see the HOMO and LUMO nicely labeled. And you'll notice here that there's this electromagnetic spectrum down at the bottom there. Those of you guys that have had physics, which I think you've all had, you'll remember that different wavelengths, right, are kind of correspond to different energies, probably. And one of the reasons that we talk about this with these conjugated dienes like hexatriene is that it turns out the more double bonds you kind of put alternating with single bonds is the narrower and narrower this gap gets, until what happens is that if you shine light on this thing, it stops absorbing it just in the UV, right? So things that have really, really small wavelengths tend to have very, very high frequencies or very high energies. So eventually, when you get photons of a certain wavelength, when you get that gap to be small enough between the HOMO and LUMO, you actually start to get colors. And if you can absorb photons of a certain color, that means the other colors are going to get reflected back at you. And so this is kind of built into a discussion of, why certain organic things are colored, right? And so like things like beta carotene, which you probably, if you ate too many carrots, you'd end up turning kind of orange. And that's because the beta carotene has this really, really long set of conjugated double bonds that absorb a lot of the kind of the lower regions here. And then so what we get reflected back at us is that bright orange of a carrot, right? And so you can see we're going to talk about this kind of off and on, so it's important to talk about. But if you're confused by it, you're not alone. It's really a tough subject. And I see my job as just kind of like showing you where it's important and then just ignoring its existence as much as possible.